So we've talked about magnetic force already, and we've kind of looked at it in two contexts. We've looked at the case of a charged particle entering an external magnetic field, and we found that the magnetic force was equal to QVB. And then, of course, we used our third hand rule to establish the link between FM, B, and V. And then we also talked about the second application of the third hand rule, the relationship between the current, the length of the wire, and the magnetic field, and also the magnetic force. So we also had this FM equals ILB. So that's for when we're looking at a wire in a magnetic field. Now, what we want to just kind of look at here is we're going to look at the case of what happens when we have wires side by side. And this was some work done by André-Marie Ampère. Now, we have two wires, we have them side by side, and you'll notice in this case the direction of the current is going into the page for both of these wires. Now, it's already showing you what the answer is, but let's just have a look at this. Let's try to rationalize this a little bit. So if I use my first hand rule, I'm going to have my thumb in the direction of the current, so I'd kind of have my thumb sort of going along the direction of the current, and I'd grasp around this wire. This would give me a magnetic field that's going around the wire in a counterclockwise direction, which is going to be the same thing here. Now, we're just kind of looking at this region that's in between our two wires. So we know for a magnetic field, we know field lines enter the south pole of a bar magnet, and we know they exit the north pole of a bar magnet. So as this field is going around counterclockwise, kind of at this point right here, this is almost like having a bar magnet with a north pole up here and a south pole down here. Whereas on the other side at this point here with the magnetic field going down, well, again, we kind of have the magnetic field entering on a south pole here and exiting on a north pole down here. At this point, what we have is it's almost, you can imagine, like the opposite poles of a magnet line. We have a north match with the south, and we have a south match with the north. So what's going to actually happen is these two wires are going to attract one another, and this was a conclusion that Ampère had drawn. If you have two parallel wires side by side, and you have the current going in the same direction, the two wires are going to attract one another. We also have the second case, so this time we're going to have wire with the magnetic field the current going into the page here, but this second wire we have current coming out of the page. So again, we've already dealt with the hand rule on this one. The magnetic field is going to go counterclockwise around the wire. Now in this case, with the electric current coming out of the wire, out of the page rather, we have our wire, we have our current coming out of the page, so if we grasp around that, that is going to give us our magnetic field going around clockwise. Same thing again, we want to look at these closest points. So at this point here, I have the magnetic field entering this hypothetical bar magnet, so this would be like a south pole and a north pole at this point. And then over here we actually have the same configuration. We have this magnetic field line entering this south pole, and we also have it exiting this north pole up here. What that's saying is that we have these north poles lined up with each other, and we have these south poles lined up with each other. We know through the laws of magnetism that like poles repel one another. What Ampère correctly concluded is that if we have wires side by side where one current's running in the opposite direction of the other, what we're actually going to find is we're going to have this repulsion. So these wires are going to experience repulsive forces. Yeah, what we want to remember is that when the currents are in the same direction, there's going to be a force of attraction between the wires, and when they happen to run in opposite directions, there's going to be a force of repulsion between them. And then, of course, Ampère, he did a lot of experimenting with this, and he also figured that magnetic force, it depends on the length of the conducting wire. We already know that from FM equals ILB. We know the distance between the conducting wires, and as well the amount of current that we're pushing through each wire. When Ampère did this experiment many years ago, these two parallel wires, this was actually how the ampere was defined. Now I have to add that this was before the changing of the SI base units last year on May 20th. So before the redefinitions of the SI units, the SI base units, the ampere was actually defined as the constant current that needed to be maintained if you had two wires side by side, assuming they were of an infinite length and negligible cross section. If they happened to be placed 1 meter apart in a vacuum, and they produced a force, whether it was attractive or repulsive, of 2 times 10 to the minus 7 newtons. So these parallel wires are how the ampere used to be defined. That is not the current definition anymore, and in fact I honestly can't tell you what the new definition is at the moment. I haven't really read up too much on it. So last thing, again, in physics, we're always key on trying to tie in real-world applications of what we learn in class, because we don't want things that we learn in class to seem like they're kind of standalone. We do want to see the greater context of this. And one of the biggest applications of what we've been talking about, like current through a wire and magnetic fields surrounding that wire, would be the electric motor. And this is also why we would have talked earlier about FM, that magnetic force, sometimes being called the motor force effect. Now, I'm just going to go over this briefly, but here we kind of have like the very basic setup of an electric motor. So we'll see the stator, which is our external magnetic field. We'll have this commutator ring. The purpose of the commutator ring is to ensure that we have the current flowing in one direction at all times. Since we're assuming this is a DC motor, we don't do AC current in Physics 30. And then of course we have our armature wire. Now what you'll notice that's really important for the armature wire is that it's bent such that the current, it's still going in one direction through the wire, but as it passes through the magnetic field it sort of changes direction, because you'll see here it's going in this direction, but down here it's coming this way. This is to ensure that the magnetic forces on different sections of the wire, they're going in opposite directions. A torque can be generated on the wire, and then that armature wire can spin, and then we can use that energy for whatever purposes we desire. So we'll see here with the current going this way, and then based on our magnetic field, again, going from a north pole to a south pole. If we do our third hand rule, we'd have our thumb in the direction of the current, magnetic field along the fingers. We have the open palm pointing up, so FM is going to be up here, and then based on the current going down this way, magnetic field towards this way, our open palm is going to point down. So simultaneously on this wire, we're going to have FM up here, we're going to have FM down here. This is going to cause the wire to turn. In an actual motor, you're going to have more than one armature wire. This is just meant to show the basics of how it works. And this is a great real-world application of this. And you can even build your own simple motor using some copper wire. You just have to make sure you strip off the coating. And just a small little battery, like a AA battery, works. And then, of course, some kind of external magnetic field. But this is a great real-world application of the things that we've studied so far.